The idea for this first tutorial is to look into phase locked loops in Max. And the overall idea that's addressed here is when we want uh, a phaser like this to have multiple of these phasers and make them not align only in frequency but also to align in phase. And there are some built-in ways in Max to handle this. For example, as you may know, we can have a transport object, and if we enable this, we can set the frequency of this phaser in musical terms, like this. And now if we have two of these, you see that they are in frequency the same, but they wrap around at different points in time. But this attribute called lock now allows us to lock the phase of this to match the transport. So as soon as I click this, you see that there was a jump in the phase, and now these two are synchronized. But there are some limitations with this because as you saw, first of all, we have this jumping behavior, and we may want something that gradually locks into a master clock or phaser over time. And then another limitation of this built-in behavior is that we cannot use the lock attribute when the phaser is set in non-musical terms, like here 0.5 hertz. You see, when we enable lock, we just start outputting 0 here. And the reason for that is that there's no concept of something to lock into here when we are free running this phaser with 0.5 hertz. But assume here that we have this phaser as a master clock, and we want to create a second phaser, and we want this to gradually lock into this first phaser. And that is where this concept of phase locked loops come in. And the way this works is that we have input phaser like this going from 0 to 1 and resetting with a certain frequency. And what a PLL does is that we, inside this PLL, have a numerically controlled oscillator, or in our case, a numerically controlled phaser that will output another phaser. Like this. And then we use a feedback control loop. So in the input here of the PLL, we have a phase comparator that will continuously monitor the difference between our output phaser and our master input phaser. And then we have some kind of control loop here that adjusts the NCP based on the error that we're measuring. And we will implement this using gen tilde. So let's call this PLL. And let's make a blank gen tilde patch here. And there are different ways to do this, but here I will use the code box operator to implement this. And the first thing that we can do is to implement this numerically controlled phaser. And that is very simple in Gen. All we need is a history object keeping track of what our phase is. And we need some parameter setting the frequency. And then what we do is that since in gen tilde we're in the sample by sample domain, so to speak, so this code is executed for every audio sample. And what we do is that we increment this phase with a value which is the frequency that we set divided by the sample rate. And now this will increment indefinitely, so we also need to wrap this between 0 and 1. So this is our NCP from the figure here. And if we output this, we should see a similar phaser in output here. And changing the frequency is changing the rate here. Very simple. Now let's move to this comparator part. And then we have an input here, which we can call X. And we compute here an error in our comparator, which is X, our input phaser, minus the phase of our output phaser. And for this control loop, it's good if this error is 0 centered. So we will wrap this value between minus 0.5 and 0.5. So this phaser is either behind or before this input phaser. Now if we make another output to output this error, we can visualize how this behaves. So now we have another outlet here for the error. Let's duplicate this. Let's make it 0 centered. Range minus 0.5 to 0.5. And then let's also print out the signal value here. So that's our error. Here is our NCP. Now you see that this error is fixed at, in this case, 0.4 something. If we start changing the frequency of our NCP, this error starts to drift over time. But as soon as we have the same frequency on the PLL as the phaser, we have a fixed error here. And this is the error that we will use now in our control loop to close the control loop. And the way to do this is, if you imagine taking the phase and then adding this error, then we essentially get X back again, right? So error is X minus phase. So phase plus error will be X again. But we don't want to do this directly, because then we would instantly lock into the phase, but rather we want a gradual control of the phase. And that's essentially achieved by updating the phase with some small value times this error. So then for every sample where this runs, we will sort of nudge the phase with this error term, and when the error term becomes 0, we are locked in. So now you see, when we did this update, this error starts dropping, coming closer to 0, and when it comes to 0, this input will be perfectly aligned with the output. Now we put a very small value, so it's very slow, but eventually it will get there. So now we have implemented everything, but we can add a couple of tweaks. One thing is that we may want to control how fast this is happening. So we can make a parameter that we call, let's say, just A. Let's make it 1 by default. And then we can make this factor here be dependent on the sample rate. So we can, instead of this small value, we put A divided by sample rate. And now a larger A will make it lock in faster, and a smaller A will make it lock in slower. Let's also clean this up a little bit. This is our comparator. This is our control. Now another thing we could add here is possibility to enable the lock-in whenever we want it to happen. So let's do this by making a variable called lock, and we have this as an input here, and then we just say that if we're in the lock state, we want to make this adjustment to the face, otherwise we don't. This needs to be input number 2. And now this means that we can here enable by creating a signal object with a toggle, so that we can toggle this between 0 and 1 like this. And we send this to the second inlet, so that whenever we enable this, we send the 1 in here, and this means that the control is enabled. And then we have also our A factor, which is controlling how fast the lock-in happens. And this is our lock enable button. So now, for example, if we change the frequency to make this drift out of phase, we see these two are out of sync, and as soon as we click lock, we gradually lock into the master phase. And if we increase this factor A, this will happen much faster. And if we decrease A to, say, 0.3, we will have a much more gradual lock-in. Now this is basically the starting concept, and you can imagine using this for various different type of things, like having LFOs that lock into each other, or if you have phasors driving sequencers, we can have them go out of phase and then slowly back into phase again. But that's it for this first part, and in the second part we will look at some use case of this type of technique. So thanks for watching.